Right, so here we go. Type 2 metals is the next thing that we need to talk about, and we'll give you, or I'll go through a couple of those examples with you in the packet that you should be working on. The first thing we should do is kind of figure out what a type 2 metal is. And it's a little bit different than a type 1 metal. Well, it's actually a lot of bit different from a type 1 metal. So let's talk about, first of all, what a type 2 metal is. How do we define it? What metals are type 2 metals? And then we'll get to the business of naming them and finding their compounds. So if something is not a type 1 metal, it's a type 2 metal, right? It's not hard to figure this out. If something is a type 1 metal, you already have that list from the previous one. And maybe at this point, if you haven't done this already, you might want to pause and put these type 1 metals on your periodic table. How do you determine if it's a type 1 metal? All you really need to know is that it's a metal with a known charge, and then a group 1, a group 2 metal, or a first column, second column metal that has a +1 or a +2 charge. And then these 4 transition metals, you need to know those for tests and things like that. So make sure that you write that down at some point. I'll give you a second to do that now. Okay, so here we are back. I have a type 2 metal. Here's a kind of a quick and dirty definition. It is a metal that has a variable charge. So these metals have variable charges, meaning it can take on sometimes 1 or 2 charges, but sometimes there can be quite a few charges. So let's look at some examples of a type 2 metal. If we go, if we go to our periodic table, I actually went to ptable.com, great website. If you ever get the chance to go there, you should. It's got so many different periodic tables on there. Well, not really so many. It's got a bunch of them, and they have different uses, but they all have super useful information. I have listed out here all the possible charges, or at least all the observed charges that we've seen in gold. And that is -1, +1, +2, +3, and +5. In blue or teal, I have highlighted the 2 most common. Most of the time, if you encounter gold, it's going to be +1 or +3 as an ion. And then I have mercury. Mercury can take a +1, a +2, or +4 charge, and the most common are +1 and +2. Lead, a very big element, but this is not truly a transition metal because it is really more of a p block. It's still, for this stuff, we'll consider it to be a transition metal. It can be -4. That's weird. That's a huge negative number for charges, but it can also be a +2 and a +4. So these usually end up being +2s and +4s. We could have platinum, PT, which could be a +2, +4, +5, or +6. And most of the time when you encounter platinum is going to be +2 or +3. Finally, if we look at, iron is next. So if I look at iron's charge, -2, -1, +1, +2, +3, +4, +5, +6. Now, a negative thing like -2 or -1 iron is not going to attract and bond with or form a ionic compound with something like oxygen, right? But the +1, +2, +3, +4, +5, +6 ones, those can. Which means that if I said iron oxide, I would have, let's see here, 1, 2, 3, 4, 5, 6 different ways that I could make an iron oxide. So that's not really clear about how we should name this. And so there's a method for naming them. But the important thing right now is that you understand that a type 2 metal could have multiple charges. It will usually take one of maybe 2 charges, 2 or 3 charges. Those will be the most common, but it could have several different charges that it could potentially take or that have been observed in some way, shape, or form. And here's that same page we were working on in the last video. I have a copper, 2, and fluorine. And we're going to mix these up somehow, and we're going to come up with a compound that's ionic, that has every element with a full outer octet, and that the whole thing is going to be neutral when I put it all together. So copper here, you might notice in parentheses, it has a Roman numeral 3, or 3 I's, right? That's, again, a Roman numeral 3. Copper, when it has those Roman numerals, that means that metal is a plus whatever that number is, charge. So if I have 3 as my Roman numeral, it means my copper, Cu, is going to be a 3 plus copper. Fluorine, we already know the charge on that. In fact, we'll always know the charge on that nonmetal. It does not change ever. Certainly not for this class. So I have a 1 minus fluorine. I have a 3 plus copper. If I do my crisscross thing, the copper gets the 1 and the fluorine gets the 3. So that I could then call this CuF3 or copper trifluoride, right? Actually, no, it's not copper trifluoride because the naming convention for this is a little bit different. And this is probably the hardest part. This is the tricky part, and it looks weird. It gets weird. And the only way to really get good at this stuff is to practice it on your own. Okay, so I know that this is an ionic compound because there's a metal. This metal is a type 2 variable charge metal. I think let's use Roman numerals to keep it consistent. So this is a type 2 metal. And the other thing that is bonding to it is fluoride, when it bonds itself. And fluoride is a non-metal. So this is a type 2 metal reacting with a non-metal. And there's again, a separate naming convention for that. If I wanted to name this, I have to do something special. If I call it copper fluoride or copper fluorine, and fluorine is incorrect, it has to be fluoride. We drop the last 3 and we add the "ide" to the end of this. But if I have some copper and fluorines, then something kind of interesting is going to happen with our chemical name. We start out just treating it like our regular old type 1 metal. So I'm going to write it as a copper fluoride. But in between the copper and the fluoride, I need to have a Roman numeral that gives me the charge on the metal. So if we had a copper 3, we would call this, to make this compound, I got scribbled out there. Okay, so if I have copper 3, to make this compound, I will need a +3 or a Roman numeral 3 in between the copper and the fluorine to tell me which kind this is. So I think, did I talk about copper in the last one? Copper is also a transition metal with variable charges. And if I look it up, let's see here, where is our copper at? If I look it up, it could have a charge of +1, +2, +3, +4. We don't know what the charge is on this, so we have to look at our fluorine and try to figure out from context how to assign the charge to this, this copper. Fluorine, on the other hand, we know the charge on fluorine. We always know the charge on this nonmetal. We know that the charge on fluorine is going to be a -1 when it forms an ion. We know that there are 3 fluorines. So overall, our 3 times -1 is -3 charge from copper. Let me write that down. CuF3, I think I said we'd have a -3 charge from copper. I'm in a -3 charge from fluorine. But anyway, CuF3, right? I will have 3 -1 charges for a total charge from the fluorine of -3. Copper, let's pretend we didn't know what it was for a second. Let's say we didn't know it was a +3. How would I figure out what the charge on copper is? Well, if I look at fluorine, it's -3. The molecule has to be overall neutral, which means that the charge I get from copper plus the charge I get from all of my chlorines has to equal 0. Or sorry, fluorines, not chlorines. For that to happen, I need a copper to balance out that negative charge. Now, this copper balancing out the negative charge, there's only one of them, right? So there's kind of like a rule. If you take the negative charge that you get from your nonmetals, write this down as a step-by-step process. So you take the negative charge from nonmetals. Not just from one of them, but from all nonmetals you're considering. Then you divide it, that charge. Basically, you divide the results from step 1. by the number of carbons, or sorry, by the number of metals. Or the number of metal atoms. So if I have a certain number of copper and I have a certain number of fluorine, I know what the charge is on fluorine. Each one's -1. Let's say I had something that was like FeF4. So for example, FeF4 has 4 chlorines. Fluorines. The total number of charges from this fluoride, actually, I should say. So if it's an ion, it gets the ide. The total number of charges from those 4 fluorides will be 4 times -1, or -4. There's only one there's only one iron, which means that this -4 charge has to be balanced out by a positive charge from our from our iron. That iron has to have a +3 charge. So we would call it Fe, and then F4. Pretty simple, right? If I want to name this thing, though, this is where the hardest probably part comes in, because it does get really, really confusing. But I notice a couple things. I notice that there's a transition metal, and I notice that there is a non-metal that I always know the charge of. I was able to determine the charge on my metal using the total charge on my non-metal. What that means for me now is I can start to build the name of this molecule. First thing I'm going to do is write down my first element, iron. The next thing I'm going to do is I'm going to write down the Roman numeral of the charge on iron. And I said if there are 4 fluorines with a -1 charge, I have to have a positive charge on my 1 iron to make it neutral. That means that I will have to have the same charge on my iron as I do on my non-metal, which will be +4. So let's go ahead and write out this full formula name. I'll do it in a different color, in red. I would start off by writing out my iron. I write in Roman numerals my charge on my iron, which is 1, 2, 3, 4. And then from there, I would write out my final element, which is fluoride. It was fluorine, but when it became a negative ion, we started calling it fluoride. So this is iron 4 fluoride. And maybe some of you who know a little bit about Roman numerals, you might be realizing, hey, there's an issue here. And this is not proper. We need to change it so it's proper. So when you do Roman numerals, 1, 2, and 3 can just be like I's, but 5 is a V, and the number before it is a V with an I before it. If that makes any sense. Ultimately, what you get is that the number, or the oxidation number of +4 is written as that. Iron 4 fluoride. IV means 4 in Roman numerals. So we would call this thing here a copper 3 chloride or fluoride. And we're pretty much done. That's it. So it seems simpler, when you have someone who kind of has an idea of what's going on, do it for you, but it does get pretty rough. So be really careful about this stuff. Be very, very careful. Follow your electrons, see where they're going to go, and then make sure that everything is, all the conditions are met for an organic compound, or sorry, an ionic compound. Those conditions, again, everything in that compound has to have a full outer octet, and the compound itself has to have the same number of negative charges as it does positive charges. It needs to be neutral. All right, last thing we need to do is figure out a way to draw a Lewis structure for copper. Copper is, in this case, a +3, so before it goes into the bond, it will have 3 negatives. So it has 3 negatives. If I lose all 3 of those, I became a +3, just like I expected. So copper and fluorine with its, let's see here, 1, 2, 3, 4, 5, 6 electrons, 7 electrons. It's going to take 1 electron from each carbon. it's each fluorine will take one electron from the copper. There are only one electron leaving the copper at a time. So if that happens, what I need is not just a bunch of stuff going on. I need 4 fluorines, right? 4 negative charges to cancel out that positive charge, or 4 neutral fluorines to accept all those electrons. Let's go ahead and draw those as well. 1, 2, 3, 4, 5, 6, and another fluorine. Maybe we'll put down here. 1, 2, 3, 4, 5, 6. All right, so this electron will go here to this fluorine. Oh, I forgot the 7th electrons on these. One of these electrons on my middle fluorine, that's going to go on my, the final electron that we're missing is going to go onto this fluorine. And now we have everything happy. Everything has a full outer octet, and everything as a whole, this thing is neutral. So I now draw my arrow to represent my before, left being before, to the right is after, and I will start writing out my chemical formula and stuff. So copper, Cu, and then the next thing, what happened? I hit the wrong button. Oh, there we go. So anyways, copper is Cu. We do not have any electrons left around it. They've all been put onto fluorines. And so we leave that outer electron shell empty. And I have now, keep doing that. What I have now is a copper, and it is going to be bonded to a total of 3 fluorines. Each, I don't like the way that looks. Let me move that Cu a little bit. Okay, try it again. I have a copper, and I will have 3 fluorines. So CuF3. That is how we do our arrows and stuff. This is how we push our electrons. This shows us what is going to accept an electron and what cannot accept an electron. It will also show us what the charge is on the ions that these things form is, or are. So CuF3, and if I want to name that, well, we already know it's copper 3 fluoride. Okay, let's see if there's any others. Okay. I don't see really any others. So I'm going to go ahead and end this video here because we don't have a whole lot else to talk about. But these are the steps that we need to take to make sure that our naming is correct and that our chemical formulas are correct. So never, ever, ever in an ionic compound should you put a prefix like mono, di, tri. All that is taken care of by the charge of the central element or the charge of one of the elements that sometimes you know and sometimes you don't. But we can usually figure it out. So, all right. That's it for this one. I'm going to close it out here, and then we'll come back and talk about one more thing, which we call polyatomic ions and how they affect chemical or ionic bonds.